Hello, Assalamu alaikum. Hello, Assalamu alaikum. Can you hear me?
Walaikum assalam, sir. Yes, we can.
Just a second. So we had this is the screen. Can you guys see the screen?
Yes, sir.
So we're going to start where we left off. We had just a quick recap of everything that we were up to. So this one, we had started talking about we did the crisscross method. Okay, that was something that we did. We talked about polyatomic ions, molecular ions. We did that. I gave you a brief idea of how polyatomic ions were formed. And we started writing all these equations. I told you that there were 9 equations that you had to do in O levels. I mean, these are the 9 important equations, ignoring all organic equations, just the basic acid-base equations and decomposition equations. So we had started talking about these equations, and we're going to learn how to make these equations. But before moving to that, we had started talking about acids and bases, just very briefly. And remember, acid bases is not really a chapter in AS. You're going to study acid and bases in A2. In AS, it's a very small component of a particular topic, which basically revolves around acids being proton donors and bases being proton acceptors. But anyways, we're going to start over here. Okay, just quickly. Remember, our goal at the moment is to make equations. And just a second.
Sir?
Yes.
Sir, I've joined very recently, so do you have any recordings of the previous classes?
Yes, I have. You basically missed just the yesterday's class. I mean, we just wrote this down that we're going to start making equations. These are mostly O-level equations. I mean, metal plus acid, base plus acid, carbonate plus acid, and all of this. So we're gonna do all of these. Okay, and
Okay.
Rafa, are you familiar with? You're probably familiar with these ions as well. We did. I mean, all these ions. You need to know what the formula of the ions are. Like an ammonium ion is NH4+1. A carbonate is CO3-2, right?
Yes,
And
sir.
so on. Anyway, so let's just start here. And so acid is a proton donor, base is a proton acceptor. I mean, this definition of an acid and a base, that definition is basically a Bronsted-Lowry acid-base theory definition. So just don't get confused. You already know this. What you just don't know is that this is part of the Bronsted-Lowry acid-base theory. This is what it's called. So we've given it a name now. In the last class, we had talked about why is H+1 so important. So I was explaining, why do you study acids and bases? Why is this? Why is some molecule? I mean, this is what an acid is. It's some random molecule that is releasing H+1 ions. So it's giving off H+1 ions. And it could give 1 H+1 ions, it could produce 2 H+1 ions, or it could produce 3 H+1 ions. If something that produces 1 H+1 ion, that's known as a monoprotic acid or a monobasic acid. So something, and I'll just write this down. So monoprotic or monobasic. That is an acid that produces just acid which produces exactly one H plus 9. So it produces one H positive ion and so on. You're going to have diprotic or dibasic acids. So diprotic or dibasic acids. So they're going to be molecules. It's an acid which produces two H positive ions, and so on. So just don't get confused when you hear the term monoprotic or monobasic, or you hear the term diprotic or dibasic. As anyways, moving on. So it's a molecule that produces H plus ions. So how can a molecule produce H plus ions? It can produce H plus ions if it has H plus ions to begin with. So what are those molecules that have H plus ions? We're going to list all those acids. So remember, these are acids, and you should know the name of these acids. These are the common ones. You're already familiar with them. So the first one is hydrochloric acid. That's it's got H plus ions attached to a Cl minus ions. It produces H plus ions when it dissociates in water. So this is HCl. That's basically hydrochloric acid. And we're going to list all the other ones as well. Does anyone know any other acid? The name and the formula of the acid.
Sulfuric acid.
Okay, so you've got sulfuric acid. That's H plus 1, and combined with SO4 minus 2. So the formula of sulfuric acid is going to be H2. So it's going to be H2SO4. So that is sulfuric acid, and let's quickly make a list of all the other acids. You've got what is this one? H plus 1 with NO3 minus 1.
Nitric acid.
Because that's nitric acid, that's HNO3. What's the formula of phosphoric acid? It's
H3PO4.
That's H3PO4. That's H plus 1 with PO4 minus 3. And so that's H3PO4. Any other acids apart from these? I mean, ignoring organic, we're not dealing with organic chemistry at the moment. Does anyone know what's a carbonic acid? That's H plus 1 that's attached to a carbonate ion. And that's going to be H2. Although that's organic, by the way. That's H2CO3, that's carbonic acid. You've got some other acids as well. You've got sulfurous acid, that's H2SO3. You've got nitrous acid, that's HNO2. And you've got phosphorus acid, which is H3PO3. So this one is sulfurous. This one is nitrous acid, and this one is phosphorus. And this one is phosphorus acids. I'm going to write down the ions because remember, you need to know the components of these acids. So for all of them, It's basically an H+1 that's combined with this one would be H+1 with SO3 minus 2 ion. This one is going to be H+1 with NO2 minus 1, and this one over here would be H+1 combined with PO3 minus 3. So all these acids and their formulas and the components, they must be known to you. So if you have a hydrochloric acid molecule, what the HCl molecule will do is that when you add it in water, or even if you don't add it in water, that's not a requirement. As long as it's capable of releasing an H+1 ion and giving it to someone else, that's what an acid is. And you have to remember the formula of these acids and what particular ions, what is the composition of these acids. Is that clear, this thing? You clear?
Yes.
Yes. Yes.
Now, the other part, let's talk about a base. A base is a proton acceptor. So it's a molecule that's capable of doing the exact opposite. So what's a base? So you've got a base, and what it will do is that if there's an H+1 that's around, it's going to grab and accept that or join it with itself. So it's going to be absorbing H+1 ions or accepting them. So what charge do you think it will have? Like why would I mean, what charge would this have that it accepts a positive ion?
Negative.
Positive charge?
Positive.
Negative, right? Because if it's negatively charged, it will attract
Okay.
H+1 ions. So there are plenty of things that are negatively charged. But the more common ones, remember there's an infinite possibility of bases. There are infinite possible acids and they're infinite possible because the definition is extremely broad. Anything that releases an H+1, that's an acid, right? So anything that accepts H+1 is a base. So it's a very broad definition. So we're gonna just be very specific about this. We'll just do a few bases. So it's probably going to be a negative ion. The first one, that's oxides. So compounds that have O-2 ions. If it's got O-2, it is capable of accepting H+1 ions, H+1 ions, and it will form water. So which compounds have O-2 ions? Metal oxides, and there's another compound, hydroxides. They're also capable of accepting H+1 ions or attracting H+1 ions. So the other one is OH-1. This would be 2H+1. They would also be able to accept H positive ions. And when they accept H positive ions, they are going to turn into H2O. Who else? You got carbonate ions, which are CO3 minus 2 ions. They're also basic because they're also negatively charged. And if there is an H+1 that's around, they will accept or attract or absorb that H+1 ion. What will happen in this case is that the H+1 will get attracted to the oxygen over here, and it will form water. So the 2H+1 will get attracted to the oxygen, which has a -2 charge. It ends up forming water, and carbon and 2 oxygens are left. So carbon dioxide is formed as a result. So this is what happens. So just very briefly, oxides, hydroxides, and carbonates are capable of accepting H+1 ions. Accepts H+1 forms water. OH-1 accepts H+1 forms water. Carbonate, if they accept H+1, one of the oxygens absorbs the H+1, turns into water, leaving behind carbon dioxide. Is that clear, this thing?
Yes.
Yes.
Okay, there's actually another base, which is, let me just write this, that now these ions will not exist alone. A negative ion usually does not exist on its own. So there must be I mean, the oxide must be a compound. So these are usually metal oxides. So they're usually metal oxides or metal oxides, metal hydroxides. Metal hydroxides and metal carbonates. Or it's not even necessarily a metal. It could be some random positive ion. So either it's going to be a metal, or there are other positive ions as well, like ammonium as well. Ammonium hydroxide would also be a base. So the oxides or hydroxides, so it would either be NaOH or KOH. Remember, the Na or K has nothing to do with it being acting as a base. It's the OH ion that's acting as a base. So whatever the ion is next to it, that's basically a spectator ion. It's not doing anything. But if this is a negative ion, the compound there's going to be one positive ion next to it. So anyways, you already know this, that metal oxides, metal hydroxides, metal carbonates are basic. There's actually one more, which is basic as well, and that's ammonia. That's another common base. Ammonia is a base as well. Because it's a molecule which we'll study later on that also accepts H+1 ions and turns into NH4+1. So ammonia is also basic. So is this idea clear that these are some common bases: oxides, hydroxides, and carbonates? TK, clear? Is that clear?
Yes, sir.
Now, coming back to the question, why is H+1 so important? Why is this fact that there's a molecule that releases H+1 and there's a molecule that accepts H+1? Why is that so important? Why is the H+1 ion extremely important? And the reason for that is that, and let me explain the reason why H+1 is so important. I wrote down the question early on, just 1 second. Let me just, so this question over here, I'll just copy this and we'll try and answer this. Why not any other ion? Why do we study H+1 so much? So that was one question that we, so this question over here. So why do we study H+1 so much, and why is pH so important? And the reason for that is that water is important. It's not H+1 that's important, it's water that's important. You're going to study this in a lot more detail in A2, not in AS. In AS, we'll just briefly just go over the concept. So water is extremely important. Why is it important? Because life on planet Earth, specifically planet Earth, we're not talking about any other place on the universe. Life on planet Earth or chemistry on planet Earth depends on, maybe on some other planet, it might depend on something else. But at least on planet Earth, chemistry on planet Earth it depends a lot, depends on water. So 70% of the Earth's crust is water. Even if you just dig a ground, you'll find water underneath. Everywhere there is water. There's no chemistry happening where there is no water. If you go to the Sahara Desert, you don't see plants growing. You don't see any chemistry happening. You don't see animals. So there is nothing happening there. Why? Because there is no water. So if you remove water from the equation, all chemistry stops. There's no reaction happening on the moon. There's no reaction happening on the. So why is water so important? The reason for that is that if all the chemical reactions that are happening in my body, water makes them possible because water provides the medium in which particles are floating around. So I've got this particle, let's call that X, and this particle, let's call that Y, right? So I've got two particles. So this is X and this is Y. The reason they can react with each other is because they can collide with each other. This will bump into this one and there might be some reaction. Some old bonds might get broken and some new bonds would be formed. But why are they able to collide? They're able to collide because they're floating around in water. In my body, all the chemical reactions, the reason they're happening is because all the molecules, all the red blood cells, all the white blood cells, all the oxygen, everything is floating around in a medium that's made up of water. My blood is water, my cells have water in them. So these particles are randomly moving around and they're bumping into each other, and which is why the reaction is happening. If I remove the water, the reaction will stop because this particle will not be able to meet this other particle. So the medium, water provides the medium. So water is the medium in which all reactions happen. At least most of the time. They can happen in the air as well, but 70% of the Earth's crust is made up of water. That's the most abundant compound on planet Earth. Is that point clear? This one, right?
Yes.
This is.
Yeah.
Now remember one thing. When you talk about water, water isn't really actually water. It's sometimes what happens is, not sometimes, very often it happens that the water molecule, it breaks down into H+1 and OH-1 ions. So what you refer to as water also contains two ions. One of them is H+1, the other one is OH-1. So imagine these particles are not only floating around in water. There's obviously H2O. So there's lots of H2O molecules. Let's move this. So there's lots of H2O molecules, but along with those H2O molecules, along with those H2O molecules that are around them, there's going to be H+1 and there's going to be OH-1 ions as well. Because during collisions, some of the water molecules might break down. And there's going to be some H+1 and there's going to be some OH ions, right? And remember, the water is not just a medium. Water is a very reactive species. If you know, water is involved in a lot of reactions. So water is not just a neutral, inert medium. It is itself involved in a lot of reactions. And it's very reactive. Metals react with it. So water is not just standing around. It's actually, if X is reacting with Y, it's also playing a role on its own. It might interfere with the reaction. So this is how the medium would look like. It will have water in it, but it will also have H+1 and OH ions. Now, in a neutral medium, this medium could be of three types. There could be a neutral medium. Now, in a neutral medium, the pH, which we call pH 7, what happens is that the H+1 quantity and the OH ion concentration is exactly the same. So in pure water, they have equal concentration. Why? Because if one water molecule breaks down, it's going to produce one H+1 and it's going to produce exactly one OH ion. Both ions would be produced in exactly the same quantity. So water breaks down, produces H+1 and OH-1. And both of them would be produced in exactly the same amount. So that is known as pH 7. But sometimes what you'll have is an acidic medium, which we call pH being. Now the acidic medium, just give me 1 second. Sorry, can you guys hear me?
Yes, sir.
So pH less than 7. Okay, so acidic medium. What's an acidic medium? What does an acid do? Acid is a molecule that if you place it in water, what it will do is, this is what an acid will do. It will dissociate and produce a lot of H+O9s. That's what an acid will do. So what will happen to your water when you add an acid to it? All of a sudden, the quantity of H+1 is going to go up. So let's assume that there is a molecule that's added, and that molecule is an acid. So the quantity of H+1 will all of a sudden start going. It will start going up. And there's going to be more and more. So let's add H+1. So there's going to be extra H+O9s that would be part of the solution. Is that idea clear, that an acid will make the water it will turn the water acidic? Is this clear?
Yes.
So I have a question.
Yes.
So if we are going to be showing the H plus and OH negative, and which will be forming the water molecule, so then why do we consider that the water molecules are going to be having covalent bonds between them and not ionic?
So that's the thing is, this is what happens. Water has covalent bonds. Here, let me just briefly go over that. Water has covalent bonds. Water has, this is what a water molecule looks like. That it's got oxygen, and it's got it's made up of two non-metals, right? So here's an H with its electron. Oxygen has 6 electrons, right? And there's another H+1. Now, if you know non-metals, right? Non-metals, they don't like to lose electrons. So oxygen needs, Rafa, how many electrons does oxygen need? It needs 2, right?
Yes, sir.
So it's going to try and pull this electron. It's going to try and pull this electron towards itself. But hydrogen normally doesn't really lose electrons, right? So what happens is that the whole hydrogen atom gets dragged towards with its electron, because oxygen is pulling its electron, but hydrogen is not. So imagine oxygen trying to pull hydrogen's electron and hydrogen not willing to give it away. So the whole hydrogen atom gets dragged and becomes closer to oxygen, right? This one as well. So that's what a covalent bond is, where the other atom is not willing to lose electrons. So they basically end up sharing electrons. They're just fighting over electrons, right? Raf, is this clear? That's a covalent molecule. Is that clear?
Yes, sir.
So what happens now is, during a collision, like it is a covalent molecule. What happens is that in water, there's lots of other water molecules. So let's say there's this one and there's another one. And let's say it's this one. So I'll explain what happens when these molecules, they collide. In water, this is what's going to happen. Here's a hydrogen atom. The nucleus is over here. And so let me remove the hydrogen over here and put the nucleus over here. There's one proton over here, right? There's a positive nucleus. Is that clear as well? There's a positive nucleus over here. Is this clear?
Yes.
Now this positive, that's a proton, that's a hydrogen proton, right? So what will happen is, you got 2 electrons. Why was this proton sticking to this? Because it was getting attracted to the shared electrons, right? That's what a covalent bond is. And if you see over here, there are 2 electrons over here as well, right? So there's a possibility that when they collide, this hydrogen proton might get attracted to these electrons over here. Is that clear? Or it might get pulled by these electrons over here.
Yes, sir.
Is this idea clear? So basically, the reason this hydrogen nucleus was attracted to the shared electron, it was obviously attracted to the shared electrons because it was positively charged, right? But when another molecule comes along, that other molecule also has electrons. And if they come sufficiently close together, this hydrogen might leave its electrons over there, and it might get pulled by the other atom. So that's how dissociation happens. And when dissociation happens, what would be the charge on this? It's going to be +1, right? Because it lost its electrons, right? Is that idea clear? Just the idea. Is that clear?
Yes, sir.
Yes.
So basically, it is a covalent molecule. That's not an issue, but this also happens with HCl. When you add HCl to water, HCl is a covalent molecule as well, but it turns into ions. It dissociates and turns into ions. Like in HCl, you've got Cl, and Cl is a non-metal. Both of them are non-metals. And here's hydrogen and Cl sharing electrons, right? Now HCl, if you know, HCl is a gas. It's a covalent molecule and it's a gaseous molecule. But if you dissolve it in water, same thing happens. The positive H and its nucleus, it might leave the Cl and it might get attracted to the electrons in the water molecule. So we'll study this in a lot more detail when we go further down and study other topics. But remember this idea that even if you have a covalent molecule, this is known as heterolytic bond fission. Like you have a bond between the molecule, like you have 2 electrons, right? But both electrons, when the bond breaks, the electrons are not divided equally. One atom gets both electrons, the other one does not get those electrons, because that other atom, instead, it leaves its electrons and it finds those electrons somewhere else. So that's known as heterolytic bond fission. We'll study that much later on. But the idea that bonds don't break, when it comes to breaking bonds, sometimes, a lot of times, they don't actually break equally. Is that clear?
Yes, sir.
And that results in the formation of ions, even though it wasn't an ionic compound, but that results in the formation of ions. So that's why water molecules, when they collide with each other, they're going to turn, and there might be some water dissociation mechanism. Just a second. So no, we don't have. I mean, there's one over here, but let's ignore this for now. But you do get the idea, right? We'll study this in a lot more detail later on.
Okay, sir.
But again, coming back to this, water dissociates, produces H+1 and OH ions. In pure water, the pH is 7. Why? Because the quantity of H+1 and the quantity of OH ions would be equal. But if you have an acidic medium, you add an acid to it, the quantity of H+1 would go up. Why would it go up? Because in an acidic medium, there's going to be an extra molecule of an acid that's added. And that extra molecule is going to release a lot of H+1 ions. So if you add any of these acids would produce a lot of H+1 ions in water, and the quantity of H+1 is going to go up. So you're going to have a lot more H+1 and a lot fewer OH ions. And what will happen in a basic medium? What would a basic medium look like? So if you have a basic medium, now in a basic medium, and you call that pH greater than 7, right? So in a basic medium, what happens is that the quantity of H+1 goes down actually. And the quantity, or vice versa, you can say the quantity of OH ions goes up. So it goes up. And this is what a base will do. Like if you add an oxide or a hydroxide or a carbonate in the water, it will accept all the H+1 ions and it will remove all the H+1 ions. The oxide will grab the H+1 ions and turn into water and so on. So a lot of H+1 ions will get used up. So like over here, if I start removing H+1 ions, let's say there's a base and that base is accepting H+1 ions. So all of a sudden, your solution will have a lot fewer H+1 ions and a lot more OH ions instead. So that's the basic idea. And why is that important? The reason it's important is all reactions are happening in water. And water is a reactive substance. Water itself plays a role. Now we've got millions and billions of reactions that are happening all the time. Some reactions, they prefer H+1 and OH ions to be equal. Maybe they need both of them. Some reactions only happen when you need H+ ions and they don't require OH ions. So they would only prefer, some reaction would prefer H+ ions to be more and OH ions to be less. And they would only happen in acidic medium. So do you know of any reaction or any place where reactions only happen when the medium is acidic? Any example of an acidic medium in the real world or in a natural system?
Like in the stomach, there's hydrochloric acid, so the pH is 2.
Exactly. So in the stomach, all the digestive reactions, digestion probably needs a lot of H+ ions, which is why you have to keep the medium very, very acidic. So your stomach has a very, very low pH because digestion requires, or the reaction requires a lot of H+ ions. And there are other reactions that require basic medium. And the medium and the basicity or the acidity or the pH of the medium is extremely important, because if you disturb that, the reactions will stop happening. Like if this X reacts with Y, maybe it needs a lot of H+ ions, so it will only happen in acidic medium. If the medium is basic, the reaction might not happen. So all reactions are in chemistry, all reactions are very sensitive to pH. You change the pH of your stomach, the reactions that are happening in the stomach will stop happening. You change the pH of the soil, the reactions that are happening will stop happening. The plants that need to grow will stop growing. Every reaction, every natural system is very sensitive to the pH. So which is why the first thing that you always check in chemistry is the pH. It's maintaining the pH is extremely important. That's why acid rain causes a lot of harm, because if you change the pH, a lot of things will stop happening, and things that should not happen will start happening. So is this idea clear, that why pH is so important? Right?
Yes, sir.
Is that clear to everyone?
Yes. Yes. Yes, sir.
Okay, moving on. Just 1 second. So now moving on, we're interested in equations only. So we'll start with the first basic equation, and that's reactive metal with an acid. So we'll just make one equation right now and do the rest in the next class. So first one, that's a metal plus. So the first one is a metal plus acid equation. And it's going to produce salt plus
Hydrogen gas.
So it's going to produce salt plus hydrogen gas. So at the moment, we'll just make or learn how to make the equation. So, and remember, this only happens with reactive metals, not with very unreactive metals. So, so I've got sodium, and it's reacting with sulfuric acid. This is how the formula, you should know if sulfuric acid is written, that's H2SO4, obviously. What would be the salt that's produced? Now, the salt produced every time would be exactly the same way. Get rid of the H, the sodium is going to take its place. And so it's going to be NaSO4. And do crisscross again. SO4 is -2, Na is group 1, so that's +1. So what is the formula? That's Na2. SO4 and H2 gas is going to be produced. Forget balancing it. The first thing is make sure you know the formulas of all of them. Every time the salt is going to be produced in all the reactions that we're going to study, the salt is going to be produced in the same way. Summer is going to come in and it's going to neutralize the acid. How is the acid neutralized? Get rid of the H. You get rid of the H, it's no longer an acid. So that's how an acid gets neutralized. So the sodium is going to come in, will knock out the H and take its place. And that's going to be Na2SO4. Forget balancing at the moment. Let's do another one. I've got aluminium with HCl. What's the salt that's going to be produced? Get rid of the H, put aluminium in its place. So that's Al and Cl. But do crisscross again. Al is group 3, so that's +3. Cl is group 17, that's -1. So the formula is going to be Al, Cl3 plus is going to be H2 gas. Is that clear?
Yes, sir.
So do me one favor. Write balance equation. I'm pretty sure you know how to balance equations with all acids that were written above. I'm going to share the board link for this one, the acid and etc. So all the notes are written over there. So I'll just quickly share. So I'm going to share the board link in the group. And that's your assignment. I'll make a Google Classroom for you to, okay, let me. Here's the board link. So magnesium with all acids. Okay, that's the assignment. Is that clear? And balance equations.
Okay, sir.
So let's continue tomorrow then. Right, okay.
Okay.
So take care, everyone.
Oh, I love it.